Uh, my name is Puneet, and I'm a PhD student in Santa Clara University. I'm the author of Virtual Bonding in Ethernet Transmission Wireless Backhaul Links. So let's start it. Very first thing is the very first thing is that what is the wireless backhaul link? So imagine yourself like sitting in a mountain, you bought a house, it's a wonderful house, and you went to your internet service provider and say like, hey, I want to talk to my relatives, so provide me internet so that I can basically watch Netflix and all. And he says that we cannot do that because there's no fiber reaching to your house. So that's gonna suck, right? So what the market has been doing regarding that is there are small players which are called wireless internet service provider. What they do is they actually have a data center right there where the fiber ends, and they shoot up some wireless links in order to provide internet to the remote areas. This is what a wireless backhaul link is, and wireless backhaul links are very useful in a scenarios where you don't want additional infrastructure or additional manual power to configure those fibers and then routers and then switches and all these kind of things. So that is what. And what is virtual bonding? Virtual bonding is to combine interfaces belong to the same machine, construct a single logical link. What I mean by that is basically consider it like a link aggregation protocol, LACP, and you basically just created a LACP link and you stuffed a bunch of interfaces in that. So since we know these two definitions now, we can actually move forward. So at present, we have technologies like DSL, T1, T3, and they are obsolete and they cannot be used to fulfill the requirement of high-speed internet connections. What I mean by that is like your home, which is within the mountains, you want to watch Netflix, but DSL, T1, and T3 will not give you the data rate to watch a 4K video seamlessly. So those are pretty much obsolete now. What they can do is in order for them to have a better internet, they can have like some other fiber or some other infrastructure to be deployed in order for you to have a better internet experience. But if they don't, then what they can do is if they have more number of users coming up to them, they can add additional infrastructure, and that will come with cumbersome manual configurations in order to accommodate the extra users. So wireless backhaul links are basically the solution here because they don't require additional infrastructure that much, and the configuration is also very minimal. So that's why, and you can have like a Gbps speed of internet. So that's why those are very popular. So now the problem with that is that wireless backhaul link have a limited capability hardware wise in order to support like more than like 3 gigabit per second data rate, and in order for you to have more than 3 gigabit per second in data rate, then they have to like do the same thing, additional hardware cost and all that. So this is going to make the internet expensive. So the solution is basically needed to be in the software. Link aggregation is a useful technique to do that, but the problem with that existing link aggregation is that the devices have to be the same. So for example, like you have two different radio links, wirelessly you can combine them. There are a lot of literature, there are a lot of research has gone into that, but they are not that intelligent in order for you to have a better solution. And what is this intelligence we will see in this paper. So those are the challenges which we faced. One is the wireless links are prone to loop, which means that the backend routers and the switches, they can also connect each other via internet, and you will have a loop. For example, BGP, multi-homing BGP. So this is one scenario. Another one is the convergence time and dynamic routing protocols is very, very high. So for example, by nature, the wireless links are very lossy. And when the Dijkstra algorithm kicks in OSPF, which is one of the dynamic routing protocols, I'm taking it as an example, what will happen is that your LSAs, when they are exchanged due to the loss, they can actually be retransmitted and you will have a more convergence time. There is no like intelligent mechanism for device failure detection. If your wireless link is broken, then you will not have internet. Somebody has to go and fix that particular link, or maybe or move the internet traffic from one link to another. The wireless links don't actually classify the multicast, broadcast, and unicast traffic. It's just a dumb L2 extension. So that is also not there. There is no automatic switch over. What I mean by that is, let's say one of your link has a SNR which is very, very bad, but you want to switch over to another one. Somebody has to actually do it manually. It doesn't detect before time, and it doesn't do it either. Currently, there is no mechanism which can segregate the transmit and receiving packets over different links. So this is also another thing. So for example, like your channel 5 in 5 gigahertz band is very crowded. So what you're going to do is basically you will have two channels, two and like let's say 8, and I'm just giving you an example. They don't have to be the exact channel which 5 gigahertz use. So 2 and 8 basically can use different multiplexing techniques. So 2 can be TDMA and 8 can be FDM, and they can transmit and receive in these two, and they don't crowd each other. So what are the concept and explanations basically we have in our solution? So we propose a new protocol. I wouldn't call it a protocol, but it's a solution where we bundle the wireless backhaul links along with overcoming the shortcomings which is mentioned in the previous slides. So the parts which we will be discussing is that those are the parts: access info packet, health monitoring system, radio info packet. Access info packet is basically a mechanism which we deployed in order for us to identify one access point as a master and the rest of the access point as a slave. Health monitoring system, and this is important by the way, I'll explain you why. Health monitoring system is something which we deployed in order for us to detect the device failure. The radio info packet is the one which is the main meat in this solution, which carries the link identifier and how the packets being routed and all. Additionally, we also have link aggregation and failover. We aggregate the link. Obviously, we have a mechanism to handle the ARP packets because there are multiple links. We don't want the backend switch to basically have corrupted routing, corrupted ARP table, and basically, have a packet gone to the wrong next adjacency. We also have a mechanism to actually handle multicast packets. Those because those are very the multicast MAC is a very special MAC, and we also have a mechanism to handle the STP traffic and the L2 traffic. We also have RF conditional switchover, which means that if your SNR goes bad, or let's say your RSSI is bad and you want to switch over, you don't have to actually do it manually. You can configure it and the links will do it automatically for you. Obviously, we're going to have a load balancing because we don't want one particular link to basically be cumbersome. So this is our header, VBBL header. Every packet, whether it's an access info packet, radio info packet, or LACP info packet, they all will have it. It's a type length value thing, which means that what is the type of whether it's a access info packet, radio info packet, or LACP info packet, what is the length and what is the value? Value will be the payload. And we also have like user entered configuration, which is VLAN ID for that particular link, and virtual IP and community string for SNMP, and probes for health monitoring, which can be either of two, TNS or ICMP. So the main important thing is the diagram here. If you look at it, this is what the physical link look like. You have three backhaul, wireless backhaul links, and those are combined with VBBL and make a single logical link. So the switch and the router in the south and northbound devices, they will see this particular link aggregation as a single link. So what is an access info packet? It's used for to determine whether it's a slave or master. So if the remote access ID, it basically carries an access ID, a 16-bit, which radio assigned to itself. And another thing which I would like to mention here is that all the configurations which we have talked about, they all go to the access point. They don't go to the stations. So station will retrieve it from there. So access ID is the 16-bit number which radio assigned it to itself, and if the remote access ID, which is the slave access point, sending it to the master one, is basically greater, then it will set it to the master. If it's lesser, then the remote will be set to the master. We also have a type of message, whether it's a request, response, or ACK. Okay. Another thing is the health monitoring system, which is done by the radio info packet. There are two types of probe, ICMP and DNS, and the reason why we chose both of them is because they are easy to implement. The default timeout for a probe is 10 seconds, but it's a lot of time, so user can configure any time he wants, like or she wants, 1 second, 2 second, or even 500 millisecond. So this is the radio info packet format looks like. It has a VBBL header. It has an associated station IP. So for example, in the right hand side, if the slave access point is sending a packet to the master access point, it will tell the associated station to the slave access point that this is the station I'm connected to, and fire rates and the link fire rates and the MAC fire rates, and those things are important for the master access point to make a decision whether how much traffic this particular link is going to bear. So another thing is the link aggregation, the failover. So as we have mentioned a couple of times, that normal LACP will not be adequate because it requires the radios to be in the same premises, which they cannot be all the time. And so our link aggregation is done by the link aggregation packet. The properties of link aggregation packet is the gateway IP, which is basically what is the next hop, the internet hop you are connected to, the VLAN ID, the port speed, and the port speed of the radio, and the aggregated link ID, which is it's assigned, and every link will have its own link ID and interface identifier, which is pretty much the hex number which you see in your if config output, and the state of the radio. Link aggregation basically is type of like two packets, port properties inquiry or response, or port properties response. It also handles unicast, multicast, and ARP and SJP traffic. So the next thing is the switchover. User can configure on what parameter this switchover can be. So if we look like in this particular packet, radio info packet, right? So we have something called SWP, like here on the bottom. So it's a 8-bit number, and you can pretty much define what parameter you want to configure, whether it's you want to have like based on SNR or RSSI or MAC rates, PHY rates. So if let's say by default it's MAC rate. So if let's say if one link MAC rates are going down, then you can shift it to another one, the traffic, and this is called the switchover, and it can be configured by user. So RSSI or any configurable user parameter you can enter. Another one is the one-way transmit and one-way receive. So if we look at the diagram here on the bottom, we have two links. One is the transmit link and another one is the receive link. The transmit link uses TDMA multiplexing and the receiver link uses FDM multiplexing. That way we can like segregate the transmit and receiver, and basically don't like congest one of the channels. So this is our simulation model. As you can see that it's multi-layer one. We can have like multiple WLAN, LAN and WAN interfaces. It only shows 3 as a diagram, but it's just a software object. It's just like a class object. So you can create like multiple of them, and it's basically multi-layer. So you can simulate anything you want. So in our scenario, we simulated like bunch of WAN and LAN, and in order to, and each of those instance signifies one wireless backhaul links. This is the experiment results. You can see that the MAC rates are constant, but the TCP throughput has increased, and we want it that way because MAC rates are very related to the power transmitted by the radio. So you don't want your radio to overheat and transmit a lot of power, right? So basically that's the reason why MAC rates have to be constant, and we should see the increase in throughput with VBBL. As you can see here that it's almost like without VBBL we have like from 600 to 675 Mbps of TCP throughput, but with VBBL we have like over 1150 Mbps. So I wouldn't say like double, but it's close to double. The another one is the one side transmit and one side receive, which we just talked about. So in that scenario also we see the almost double TCP throughput. So in our conclusion, what we concluded that with our solution, we have intelligent switchover, we have a better TCP throughput, we have a better failure mechanism, we have by probes, and we also have like a better link aggregation mechanism with slave and master in order for the users to actually have a better data rate. Now the beauty of that is that let's say if end-to-end TCP connection is established and one of the link goes down, the user would the end-to-end TCP connection wouldn't actually go out, because for the southbound and northbound device it's a logical link. So if one of those internal links goes down, the logical remains intact. So this is very important. This we also described the packet formats we used in VBBL, and we also demonstrated that we have a better redundancy in terms of wireless links. So that concludes my presentation, and if you have any questions you can reach out to me. Thank you. Bye.